Hello, and welcome to the Big Bang. In this practice problem, we will explore the concept of static equilibrium and work on finding the angular momentum of the rotational inertia for a body. Picture a general body. There are two equal and opposite forces acting on this body along different lines of actions. Let's have their lines of actions be 3 centimeters apart. Does that remind you of anything? They form a couple. When we have a couple, we can take the moment about any point in the body and get the same result for that moment. Given that this is all we know about the system, what can we do to make the system be in static equilibrium? Let's start by finding the moment resultant from this couple. We know that we can find the moment by taking the cross product of the force and the moment arm. We can then multiply the 0.03 meters by the 2 newtons and get 0.06 newton meter as the answer. The direction of the moment is counterclockwise. You can easily get that by using the right-hand rule. To put the system in static equilibrium, we would then need a reaction moment of the same magnitude, 0.06 newton meter, in opposite direction, clockwise. This way, we would stop the system from accelerating and have it be in static equilibrium. Part 2. We can now find the rate of change of angular momentum. Let's assume the body we drew has a mass equal to 4 kilograms. The rate of change of angular momentum equals the moment of inertia times the angular acceleration by definition. Turns out that, also by definition, that equals the sum of all moments. Well, this makes the solving of this problem quite straightforward. We already know the sum of all the moments. That equals 0.06 newton meter in the k-hat direction. We can now go on to part 3 of this video. We will now approximate this object as being made of 10 particles. Each particle will have a mass of 400 grams. Let's also assume that each particle is 2 centimeters away from the center of rotation of the body. The question now is, what is the rotational inertia of the system? All those assumptions actually give us all we need to know to calculate the system's rotational inertia. The rotational inertia can be found by taking the summation of the mass multiplied by the distance from the center of rotation squared for every single particle. Since we have 10 particles, we can multiply mi times di squared by 10. We then have 0.4 kilograms times the 0.02 meters squared times 10. Our final answer is for the rotational inertia turns out to equal 0.0015 kilograms meters squared. Hopefully this gives you some intuition on how to approach these kinds of problems. Let's explore more questions related to this system in the next video, and I will see you soon.